So now that we're looking at reactions of dissolving, we want to add kind of some layers of how does this interact with the other types of reactivity we've talked about and couple some equilibria together. So when you dissolve something or put it in solution, that some chemical reaction can occur, the one you want to occur, the one you're thinking about, but other reactions can still occur at the same time. So multiple equilibria exist in a given solution. So we've looked at, for example, dissolving magnesium hydroxide, and that creates hydroxides, right? You know, when the magnesium hydroxide dissolves in solution, it makes some hydroxide. Well, those hydroxides affect the pH. We know that if you put hydroxide into solution, hydroxides and hydroniums that are formed in any solution of water are going to interact with each other, and you'll make some waters, right? You'll balance out that, you'll change that balance of hydronium and hydroxide. You're going to affect the pH. Conversely, if you change the pH of a solution, it's going to change that balance of hydroniums and hydroxides. There's a different number of hydroxides in solution, which is going to affect the equilibria of the dissolving of magnesium hydroxide. So we know magnesium hydroxide affects pH. We didn't really talk about that as coupling of equilibria, but now we can see the other way also, that if we change the pH, we're going to affect how much hydroxide is in solution, which how much hydroxide is in solution affects the solubility. So we want to figure out how do we combine these different reactions together? How do we think about these reactions interacting with each other and make predictions about it? So one of the things we're going to need to do is modify and combine chemical equations to define a new reaction that has a new equilibrium. So we're going to be changing chemical equations, and that's going to affect the equilibrium constant. So we want to remember there's three ways that we can change a chemical equation that affects how the value of the equilibrium constant. If we reverse a reaction, we invert the constant, right? We had reactants going to products, we change it to be the opposite direction. That's going to invert the equilibrium constant. If you change all the coefficients, that's the same thing as scale. If you scale the coefficients, you multiply your equilibrium constant, or no, sorry, you raise the equilibrium constant to that factor, right? So if you multiply all of your coefficients by 2, you square your equilibrium constant. And if you add two reactions together to make some sort of sum reaction, you multiply equilibrium constants together. So with that in mind, let's do an example. What is the pH of a saturated solution of magnesium hydroxide? We know that magnesium hydroxide dissolves into magnesium 2+, and the two hydroxides. And for this, KSP is 1.8 times 10 to the negative 11.
All right, so what is the pH, our old friend, of a saturated solution of magnesium hydroxide? So we know if we want the pH, that comes from negative log of hydronium, right? So this would be a question of, okay, so I have this magnesium hydroxide. I want to know how it's affecting acid-base chemistry inherent in water. This is kind of something we've already seen, but we're just going to be using the KSP. So these are coupled equilibria that we've seen before, but we're basically going to kind of look at the dissolving first and then see how that will affect the kind of the acid-base, the hydronium hydroxide equilibrium inherent in water. And so basically, in order to get this, we know that that can come from the concentration of hydroxide, which is going to come from this dissolving. So if I want an amount of hydroxide, that's an amount of a product at equilibrium, because the reaction is reactant favored, that KSP is pretty low, I need to use an ice table to figure out how much hydroxide there is in this dissolved solution. So nice, that's a solid, so it doesn't matter. My ion products get zeros. Shift to the product side, keep that coefficient, so x and 2x. So then I can plug those into KSP. I get the x from magnesium. I get the 2x from hydroxide. which is raised to the second power because the KSP also shows that too. And so then I get that the KSP is 1.8 times 10 to the negative 11. So that would be x 4x squared, then the x goes in. So 1.8 times 10 to the negative 11 is 4x to the third power. I want a hydroxide concentration, so I need to solve for x. So I can divide by 4. And I need to get rid of this third power. So what I can do is take the third root of both sides, a similar square root, but it's to the third power. Cube root would be another name for it. And I would get that x is the third root of 1.8 times 10 to the negative 11 divided by 4. For taking third roots, if that may be a function on your calculator, you can also take roots using fractional exponents. So another way to write this would be the same 1.8 times 10 to the negative 11 divided by 4. Take the whole thing to the 1/3 power. Those mean the same thing. The third root is the same thing as taking it to the 1/3 power. So 1 over whatever. The square root with the square root, so 2 up there would be a 1/2 power. If you were taking it to like the 8th root, it'd be 1 over 8 up here, whatever it is. Whatever it is, those just give you a number, and you would get that x is equal to 1.7 times 10 to the negative 4th. The concentration of hydroxide is equal to 2x, so that's equal to 3.4 times 10 to the negative 4 moles. So if you put magnesium, just solid magnesium hydroxide into water, enough for it to reach saturation, so that you have precipitate, right, that you have solid left over. So you have this, as much as dissolved as possible, the concentration of hydroxide would be 3.4 times 10 to the negative 4 molar. So this equilibrium basically happens, right? This equilibrium happens, you have this dissolving, and then that's going to feed into your hydronium hydroxide equilibrium, which will inform how the acidity of the solution changes. So we can relate those using the fact that Kw is equal to the concentration of hydroniums times the concentration of hydroxide. So we could get that the concentration of hydroniums is Kw divided by the concentration of hydroxide. And so what we can do is we can go and plug those in. Kw is 1.0 times 10 to the negative 15. Concentration of hydroxide, we just calculated, is 3.4 times 10 to the negative 4th. We do that, we get that the concentration of hydroniums is 2.9 times 10 to the negative 11 molar. And see what happens is the salt, your magnesium hydroxide, dissolves, makes some hydroxides. That action affects another chemical equilibrium, namely hydronium hydroxide equilibrium. And since you make hydroxides, the hydroniums go down, and then we can compute that or kind of look at that in the pH. We have log of the concentration of hydroniums, plug in our 2.9 times 10 to the negative 11, and we would get that the pH is 10.5. So if you have a saturated solution of magnesium hydroxide, pH is 10.5, we'd certainly predict this to be a base because it is a hydroxide. Not a very good base. You're limited. You can't really make this solution. You cannot make a solution more basic using just magnesium hydroxide because you have hit saturation. That you have fully dissolved it. This is fully dissolved, so you've affected the acid-base chemistry as much as possible, and that's what it is. And so how we kind of do this work of kind of figuring out this equilibrium is we basically kind of, well, what reaction happens? This doesn't happen a lot. KSP is 10 to the negative 11, but it's more than 10 to the negative 14. So this reaction happens kind of primarily or has a bigger effect on the hydroxide amounts. And then kind of the hydronium hydroxide, the water equilibrium responds to it. that is reflected in solution properties, namely pH.
So dissolving magnesium hydroxide affects the pH. It affects that hydroxide hydronium balance that's going on in the solution. Well, simultaneously, if you change the solution, you affect solubility. If we look here at our magnesium hydroxide dissolving, we can see that on the product side is hydroxide. So Le Chatelier's principle says that if we add an acid, the acid would react with my hydroxide, decreasing the concentration of a product. If we decrease the concentration of a product, the equilibrium will shift to replace it, meaning more will dissolve. So we could functionally increase the amount of magnesium hydroxide that dissolves by adding an acid. So what is the solubility of magnesium hydroxide at pH equals 2?
So we want to know the solubility of magnesium hydroxide at pH equals 2. So this is kind of the opposite direction of what we did previously. Previously, we just had pure water. We dissolved some magnesium hydroxide into it. What was the pH? In this case, we're using something else to drive the pH, namely an acid. We've made it, it's in an acidic solution. So how is that going to affect the solubility of my magnesium hydroxide now? The magnesium hydroxide equilibrium is still going to be the same. What's going to be affected is the amount of hydroxide. Just like we saw previously in the autoionization, where the concentration of hydroxide was affected by magnesium hydroxide, and then the hydronium responded to that. The concentration of hydronium responded to the effects of the magnesium hydroxide. Here, magnesium hydroxide dissolution is going to respond or kind of deal with the change in the pH, namely the hydroniums that are there. So what we want to figure out is basically what is the concentration of hydroxide going to be if this is the pH. So we know that the constant pH is equal to 2, and we know that the concentration of hydroniums is going to be 10 to the negative pH. That's our general equation. So in this case, 10 to the negative 2 is 0.01 molar. And so we can use our same Kw equation, tells us that the concentration of hydronium times the concentration of hydroxide is equal to this Kw value. And so the concentration of hydroxide in this solution can be Kw divided by the concentration of hydronium. We can plug in those values, constant for Kw, and then the 0.01 we just calculated. Tells us that the concentration of hydroxide for a pH equals 2 solution is 1 times 10 to the negative 12 molar. So the concentration of hydroxide is going to be really, really low. The concentration of hydroxide is going to be really, really low in this case. And so what we want to figure out now is, okay, well, if this is what the concentration of hydroxide needs to be, how is the magnesium hydroxide going to dissolve kind of to describe that? And so we know for our KSP for the magnesium hydroxide, that's going to be equal to the concentration of magnesium times the concentration of hydroxide squared. Normally we think about these two ions coming from dissolved solid, but in this case, hydroxide comes from right there. The hydroxide is in solution because of the acid-base chemistry, because it's pH 2. And so, we can imagine, make a little bit of approximation that the concentration doesn't change. You're just at this pH 2, right? You're using a bunch of acid, you have enough acid to maintain pH equals 2, whatever you're looking at. And so what we would do then is plug that value in. We can also plug in a value for KSP. We would get 1.8 times 10 to the negative 11 is equal to the concentration of magnesium that needs to be in there, times 1 times 10 to the negative 12 squared. Or that the concentration of magnesium in this solution needs to be 1.8 times 10 to the negative 11 divided by 1 times 10 to the negative 12 squared, which is equal to 1.8 times 10 to the 13th mole. So what this is telling us is that if a solution is at pH equals 2, so if the solution is locked at a pH of equals 2, that means the hydronium hydroxide equilibrium is kind of locked in, and the dissolution equilibrium of the magnesium hydroxide will depend on that. This product always needs to be equal to this constant. It doesn't matter where these ions come from. In any given solution, they have to be equal to this if it's in equilibrium. And so at the point in time when you're at pH equals 2, the hydroxide concentration is locked at 10 to the negative 12, super low, right? And as a result, the magnesium concentration would need to be huge to reach equilibrium. So this is stupidly big. This is never going to happen. Functionally, what this means is that magnesium hydroxide just becomes soluble in acidic solutions. The more acidic it is, the more soluble it becomes, right? This is so crazy big. And actually what we could do, this would be like 1.8 times 10 to the negative 13 moles of magnesium per 1 liter. So we know that, it's like 1 mole of the magnesium hydroxide per 1 mole of just those magnesium ions, which would mean that you would need, that should be positive. Oopsies. So that would mean that you get 1.8 times 10 to the 13 molar magnesium hydroxide. That would be the nominal concentration you would dissolve that much. And that's just not going to happen. But what we can start to see is that if you can affect and change the observed phenomenon. This equilibrium constant doesn't change. Functionally, it looks soluble because you're not dissolving into pure water. Hydroxides are there or affected by this other equilibrium, and it affects the observed solubility. So, this makes sense. Magnesium hydroxide is a base. We would expect it to react functionally with the hydroxides that are present there and do that equilibrium, right? In order to get this pH 2, you had to add some acid. We expect the base to react with that acid. And so we would expect to kind of see this happen, see a ton of dissolved magnesium produced as a result of this, which is consistent with what we're seeing here with this crazy high solubility. It really is not something you're ever going to functionally achieve. This is impossible to reach. Really, what it just shows is you would dissolve, you basically can dissolve, just become soluble.
So we are now able to predict that you would get this huge solubility, right? You have 1.8 times 10 to the positive 13th molar magnesium hydroxide. That's how much you could get to dissolve. Now this is impossible. Functionally, basically magnesium hydroxide is just soluble in acidic solutions. You're not going to get that much dissolved, that concentration, but you are going to get basically as much as you want to dissolve. You can't achieve a concentration that high. It's a lot more than that many moles is a lot more than one liter. But you can dissolve as much magnesium hydroxide functionally as you want. Magnesium hydroxide also is going to start to lower the pH, so there's more complicated things to actually making these things. But if you could keep it pH 2, you could dissolve as much magnesium hydroxide as you want. And so if we want to think about kind of having a picture of what's going on here, we know that magnesium hydroxide, we put a solid in our solution. Some of it dissolves, not much because that's really low saturation, right? 1.65 times 10 to the -4 molar. Not much is really getting out into solution. If my solution is neutral, right? If I have kind of pure water as my solvent. If I change it to now being an acid, acidic solution, now there's hydronium present. So if I have an acidic solution that I'm dissolving into, when the magnesium hydroxide dissolves, the hydroxide immediately reacts with any sort of hydronium that's present, and the hydroxide is gone. And now I have a QSB that is too low. I'm not in equilibrium. I can see that I have no dissolved hydroxides, right? There's no dissolved hydroxides as it stands. So I have to have more dissolving. I have to get more hydroxide out into solution. So more of it dissolves. Now I have hydroxide in solution. I can have equilibrium again. And if I was at a low enough pH, i.e. there was a lot of hydroniums, boom, those are gone as well. And my reaction would continue to dissolve. And more of the solid magnesium hydroxide will have to dissolve out into solution to replenish it. And so I get more and more out there. And so this is how I functionally lead to this higher solubility, because there's more of the solid that's gone. Importantly, I'm not changing the equilibrium, because equilibrium says, you know, this saturation is low, KSP is low, so I should not have a lot of magnesium and hydroxide out in solution. And what I have functionally done is removed the hydroxide from the solution via another reaction, namely acid-base chemistry. So the hydroxide is out of solution, and I'm basically just I'm feeling there's a lot of magnesium dissolving, and the solid is gone, but I'm not changing the underlying chemical reaction. The equilibrium is still true. I should not have a solution with a lot of magnesium and a lot of hydroxide. I've just changed the solution in such a way that that hydroxide all goes away. And importantly, this is what we predicted with the Chaliers. This isn't new insight, but it is important that we can now quantitatively predict it. We can put some numbers behind this, and it's also good that our prediction is consistent with the Chaliers principle, right? All of this is kind of going hand in hand. All right. No questions for participation 320 in this video. The streak is over. We are over halfway through this set of videos. Got a couple more left. There might be some more questions. We'll have to find out. I'll see you in the next video.